welcome guys back to today's video. So today our section is going to be on inverse transform. So basically I can say we have basically concluded all the basics you need to know about Laplace transformation. Now we're moving on to the inverse transform. Now this is basically just the opposite of Laplace transformation actually, because this inverse transformation turns the function of s back to the function of t. It's very simple. So like I said, it turns the function of s of the Laplace transform back to the function of t. We all know that, for example, the Laplace of cos at, actually, we all know that the Laplace of cos at gives me s divided by s squared plus s squared, right? Now this is the Laplace of cos at. So inverse transform is actually telling us how we can change this back to this, right? You know that we have been treating is the Laplace of this back to this. So inverse transform changes the function of s. You can just basically say that the inverse transform it's a process of turning fs to ft. This, I broke it down in this way so that you can easily comprehend what it's all about. So it's not actually something very complex. It's something very simple. Now I'm going to take one example. For example, we all know that Laplace of sine at is equal to a divided by s squared plus a squared, right? This is Laplace of sine at. So now, if we want to say find the inverse transform, for example, we are given only this and we have to find the inverse transform, we can just basically say L inverse L raised to power minus 1 of a divided by s squared plus a squared is equal to what? Sine 80. So this is what we call, this here is what we call the inverse transform of Laplace. So now this basically is just a reciprocal of the inverse of Laplace of L. It's just basically the inverse of Laplace, not a reciprocal. Some people might think that it's a reciprocal because it's L raised to power minus 1, and okay, that means it's 1 over L sine 80. No, it's just the inverse of the Laplace transformation. It's not reciprocal. So this here is what we represent as inverse transform. So now let's proceed to the examples on how, basically just basic examples so you can easily understand what the inverse transform is all about. You see this example we have in front of us. It said find the inverse transform of 4 over s, right? Now this is a function of s, right? And they're asking us to get it back to the actual form or actual function of t it was before the Laplace was carried out. So this is how we find the inverse transform of Laplace transformation. So now this is 4 over s, right? We all know that the Laplace of a constant is that constant divided by the function of s. So if you are asked to find the inverse of the constant divided by the function of s back to the actual function of t, back to the actual function or the actual constant, this is basically how we carry out the inverse transform. So now L inverse of 1, we all know that Laplace of a is a over s, right? So turning this back to this is what we're just going to have. We're just going to be only having the constants, right? So that means the inverse transform of 4 over s is equal to what? 4. As simple as that. So I'll advise you to go and watch the previous videos, which I'll actually drop on the link above, on the link above, so that you can actually check out the previous videos I did on how to get the Laplace of a constant, Laplace of sine function, cosine function, hyperbolic functions, and so on and so forth. So when you've watched those videos, you can easily understand how to carry out inverse transform. So now let's take another example which says find the inverse transform of 1 divided by s minus 2. Now we are asked to turn this function of x back to the original function of t. Now, like I said, you have to remember the Laplace of these functions so that you can easily know how to get their inverse. So we all know that the Laplace of exponential at is equals to 1 divided by s minus a, right? So basically they are asking us to get the inverse of this, right? Back to the original function, back to the original exponential function. So how are we going to do it? The constant here, when we compare this to this, the constant here is 2, right? So that means, and the exponential function is exponential of the constant times t. So that means the inverse of this function here, this function of s here, is equal to the exponential of 2t. So now I'm going to take one more example, then we start treating more of the. Let's just move forward after we take this last example. So for example, we have to find the inverse transform of s divided by x squared plus 25. Now, if you look at this very easily, you all know that you will know that this is a cosine function, right? So now, the original function is actually a cosine function of t. So this function of s here, they ask us to find the inverse of this function of s. How are we going to do it? Now, like I said, you have to remember the actual function of how to carry out the Laplace of all those standard functions in order to understand the inverse function. So basically, you all know that the Laplace of cos at is equal to s divided by s squared plus a squared, right? This is the Laplace of cos at. Now, if you compare this to this, you see that they are actually the same function of s, right? But now, the constant here, when we compare this to this, when we compare this to this, that means a squared is equal to 25, right? So if a squared is equal to 25, that means if a squared is equal to 25, that means a is equal to 5, right? So now, to take this back to the original function of et, which is a cosine function of t, will be equal to cos the a, which is 5, right? Cos 5t. So I hope you guys understand this first stage of how to get the inverse transform of Laplace transformation.